So we've gone through the worm-like chain model. Now we want to go through a different way of looking at DNA, and that's through DNA elasticity. So remember our initial diagram where we said that DNA could also be modeled by entropic springs? This entire section is going to be dedicated to that. So we're going to try and relate chain elasticity with the worm-like chain model and see if we can get different properties from that using some mathematical analysis. The first step to looking at DNA elasticity is to go through the random walk chain model. So let's first figure out what this random walk chain model is, and we always start off with a grid. So we have just assume a grid like this. And we can consider this our x-axis and this our y-axis. And so when we take a look at any particular chain, we can assume it starts here. Maybe it goes across this way, towards the right, then one step up. Then from here, it can either go left, up, or right. And let's say it goes this way. And then we just keep on going. So there would be a start and an end. And let's say that for our particular model, we have n number of steps that are allowed. So in this case, let's take a look at the displacement. So with displacement, we have our x-axis and our starting point, which was here. And the idea is that, now this is a completely separate case, but the displacement is the distance from start to finish. So for the same n steps, you should have the same distance that's traveled from start to finish along the x-axis. Another thing to keep in mind is that the displacement is going to be different depending on your chain and where it ends up being. So if you start here, so this is another example. How many steps do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we have 9 steps, for the same 9 steps, you'd end up from this start to end and have some x distance between the two of them. But for another random walk, we start here. We could go 1, 2, 3, 4, 5, 6, 7, 8, 9. So here in this case, our x is completely different than the example we had before for the same n number of steps. So this random walk chain model, when we look at start to end states, it isn't very accurate, so we have to find a different way of measuring these. So then we take a look at the multiplicity of the random walk model. So we're going to look at the multiplicity, which we've defined before as W, capital N, and little n, where n is going to be the number of steps. Number of steps. To the right, and n as the number of steps to the left. So that means for multiplicity we have W and n is equal to n factorial over n minus n. And apologies, this is going to be n minus n being the number of steps to the left. N is going to be the total number of steps. But from here, we have displacement x being equal to n minus n. So x is equal to 2n minus capital N, little n is equal to x plus capital N divided by 2, and we have n minus n being equal to n minus x divided by 2. So therefore, from this, we have W and n being equal to n factorial divided by x plus n over 2 factorial and n minus x over 2 factorial. So this is just another way of representing the multiplicity of the random walk model, just in terms of displacement. So when I take a look at this, when n is a lot greater than 1, what happens? So let's take a look. When n is a lot greater than 1, then we have a constant. We have W being equal to e to the power of negative 1/2 x squared over n. So you don't have to know how to figure that out yourself. This is what we're going to base our further calculations off of. Now we're going to take a look at what happens if each step is given a length of b. So what is the multiplicity with step length b? So that means W and n is going to be proportional to e to the power of negative 1/2 x squared over n b squared, and that's going to be equal to e to the negative f and n divided by kbt, where f and n, the free energy, is going to be equal to 0 minus kBt ln of W. Okay, so we have this multiplicity term, an expression. Now we want to be able to do something else with it. We're going to compare. We're going to compare this to a spring. So remember our entropic spring models from before for DNA? We now want to compare 1/2 x squared over nb squared times kBt versus 1/2 kx squared. We're going to say K is the spring constant of a mechanical spring so we have this here. So can we rewrite the term 1/2 x squared over nb squared times kBt as something to do with a spring constant? So here, what if we rearrange 2 1/2 kBt over nb squared x squared. Then this part can be called K EFF, or the effective spring constant, kBt over nb squared. This is the effective spring constant of DNA. So the key thing from the slide is basically, from our expression for multiplicity, we end up with the term with nb squared at the bottom. And essentially, we can compare that term with that of a mechanical spring, and then call all of the outstanding variables and parameters efficient K, or effective spring constant. So then, suppose we have an entropic spring that is pulled by an external force. It means we have some sort of F force acting on it. What can we do here? We can balance the restoring force with an external force F. So therefore, we have K EFF x being equal to F, and we can define x as F over K EFF. Therefore, our displacement is going to be proportional to the applied force. So here our attempt was just to relate displacement with applied force. So moving on, this is something that, once again, these models, I won't test you on these models, but it is good to take a look at them to see how they can be used and what kind of properties we can get from them. So here, in 1995, J. Marco and E. Siggia discovered that there's this model with a whole bunch of terms. Let's try and determine what this even means. First, let's draw some sort of entropic spring. So we have something like this. We have a length L for your string, and you have your displacement from start to finish. So from here to here you have x. So in terms of these variables, you have LP, which is your persistent length. You have x being the horizontal linear displacement of DNA. You have F being the external force applied on the system, and you have L being the length of your DNA chain. So what Marco and Siggia discovered was a relationship. They discovered that the persistent length multiplied by the force divided by some sort of entropic term, kBt, is equal to a quarter of 1 minus x over L to the power of -2 minus a quarter plus x over L. So from this model, we're able to find an expression for the effective spring constant of DNA. Instead of saying it's kBt over nb squared, where it's some sort of step size b and we have n being the number of steps, we want to be able to find a different way of expressing KEFF through more entropic terms and persistent length terms that we've become used to. So from this equation, we want to determine what happens if our f is very small. So if we assume a small f, what's going to happen is your 1 minus x over L to the -2 is going to be approximately equal to 1 minus -2 x over L. So you can try to show this yourself if you'd like, but I won't go through it. Then you have 1 plus 2x over L if we assume x is a lot smaller than 1. So from here, we can say x over L is approximately equal to 2 LP over 3 KBT F. And we know from before that KEFF is equal to KBT over NB squared. So we can say KEFF can be defined as 3 KBT over 2 LP times L. So this is if B is equal to 2 LP. So now we're trying to connect the two together. If B is equal to 2 LP, then we're going to be able to replace this term with LP. And if we assume L is equal to NB, then we'll be able to replace the N. And then we rearrange the two equations, and we'll be able to get another expression for KEFF. So therefore, KEFF is equal to this, or we have KEFF being equal to 3 KBT over LB. So these are just two different ways of expressing the effective spring constant of DNA. So two alternatives that we can use. So the next part is trying to figure out what happens when our force is really large. So for a large F, we can assume that the displacement is going to go towards L. So that's going to be a fully stretched spring, which makes sense. We also know that B is equal to 2 LP. So for a large F, x approaches L. That doesn't require too much of an explanation because we apply a large force. The entropic spring is going to be fully stretched to its maximum length L, so your displacement is going to go towards L. So the next thing we want to do is take a look at some entropic spring with a start and an end. And we're going to cut all of this up into persistent lengths. So let's consider these to be persistent lengths. So that's the maximum length that these can be considered straight lines. So we have something along that. This is 1 LP. We take a look at B, and B is going to be between it's going to be approximately 2 LP. So I know this isn't totally accurate, but what this is saying is our step size B is approximately 2 LP. Anything past this refers to a random direction of movement. So, to reiterate, the step size basically tells us which direction we're stepping in. Although we have a persistent length of a certain length, for it to be straight, the step size is not going to be a measurement of how straight or bent a rod is. It's going to be a directional measurement. So our persistent length over here, as an example, B is really close to 2L. Over here, not so much. B is no longer very close to 2L, but if we consider 3L, then the direction is very much different. It's going upwards versus towards the right. So all this is saying is that in order for us to consider a step size, we can only consider up to a maximum of 2 persistent lengths. So with the worm-like chain model, there's also something else we should take a look at. And that's a force versus x over L graph. And for a worm-like chain model, the greater the force you apply, the greater the displacement. So we're going to take a look at that in a bit more detail. So this slide is titled A Balance Scale because we're going to be taking a look at chain entropy. And so we have probability of a certain length being equal to L over LP. So we have a probability distribution that kind of looks like this, and we call this the chain entropy. And we want to make sure that energy and entropy are balanced. So let's say the higher probability of DNA step sizes per length where energy and entropy are balanced. So I just want to write this down because through the graph we can explain or label this peak, which is approximately 0.08, and this is approximately 3.4, which seems like a familiar number. We're going to go through that in a bit. This is the point where energy and entropy are balanced. And at whatever point the energy and entropy is balanced, there's going to be a higher probability that there are more step sizes available per length. So then this is going to be the number of step sizes per ring of your DNA.